Name of topic QAM and MSK modulation technique of digital communication. Subject is the principle of communication. In digital communication, QAM modulation technique is the quadrature amplitude modulation technique. In this modulation process of converting digital data or low pass analog signal to baseband or high frequency analog signal. So this is the modulation in the QAM technique. Process of changing one of the characteristics of an analog signal, typically a sine wave, based on the information in a digital signal. Now, sine wave is defined by three characteristics: amplitude, frequency, and phase. So these are the three characteristics of the sine wave. First one is amplitude, second frequency, and third one is phase. So digital data or binary 0 and 1 can be represented by varying any of the three these parameters. Types of digital to analog modulation. So digital to analog conversion, there are different types. First one is amplitude phase shift key ASK. Second one is the frequency shift key FSK, and third one is the phase shift key PSK. The combination of ASK and PSK is the quadrature amplitude modulation, that is the QAM. So the quadrature amplitude modulation is the combination of amplitude shift key and phase shift key. So what is quadrature amplitude modulation QAM? Quadrature amplitude modulation or QAM is a form of modulation which is widely used for modulating data signal onto a carrier used for radio communication. It is widely used because it offers advantage over other forms of data modulation such as PSK, although many forms of data modulation operate alongside each other. Quadrature amplitude modulation is a signal in which two carriers shifted in phase by 90 degree and modulated, and the resultant output consists of both amplitude and phase variation. In view of the fact that both amplitude and phase variation are present, it may also be considered as a mixture of amplitude and the phase. This is the block diagram of QAM modulation technique, in which a converter and generally a oscillator that is generate the carrier frequency signal, and converter generate the signals in the form of digital, and these both signal are multiplied in the 2 multiplied by the 90 degree phase shift, and the output is the summation of 2 multiplier, and the output waveform is the form of QAM modulation, and there are different presentation of QAM modulation in the form of different waveforms. So in QAM, the purpose or on the base of application is in many radio communication and data delivery application. However, some specific variant of QAM are used in some specific application and standard. For domestic broadcast application, for example, 64 QAM and 256 QAM are often used in digital cable television and cable modem application. In the UK, 16 QAM and 64 QAM are currently used for digital terrestrial television using DVM, digital video broadcasting. In the US, 64 QAM and 256 QAM are the mandated modulation scheme for digital cable as a standard by the SCTE in the standard ANSI and SCTE 07-2000. In addition to this, variants of QAM are also used for many wireless and cellular technology applications. So these are the some application of QAM modulation. QAM appears to increase the efficiency of transmission for the radio and the communication system by utilizing both amplitude and phase variation. So these are the some advantage of QAM modulation technique. But there are some disadvantage of QAM. More susceptible to noise because the states are closer together so that a lower next disadvantage level of noise is needed to move the signal to a different decision point, and the receiver for use with phase or frequency modulation are both able to use limiting amplifiers that are able to remove any amplitude noise and thereby improve the noise reliance. This is not the case with QAM. Next, the second limitation is also associated with the amplitude components of the signal. When a phase or frequency modulated signal is amplified in a radio transmitter, there is no need to use linear amplifiers. Whereas when using QAM that contains an amplitude components, linearity must be maintained. Unfortunately, linear amplifiers are less efficient and consume more power, and this makes them less attractive for mobile application. So there are these some disadvantage of QAM modulation technique. This is the diagram for QAM. This diagram is the constellation diagram. So quadrature amplitude modulation QAM, when used for digital transmission for radio communication application, is able to carry higher data rates than ordinary amplitude modulated scheme and phase modulated scheme. As the phase shift key, the number of points at which the signal can rest, the number of points on the constellation is indicated in the modulation format description. And for example, 16 QAM use a 16 point constellation. When the using QAM, the constellation points are normally arranged in a square grid with equal vertical and horizontal spacing, and as a result, the most common form of QAM use a constellation with the number of points equal to power of 2 or just 2, 4, 8 and 60. By using higher order modulation format, more point on the constellation, it is possible to transmit more bit per symbol. So the points are closer together and they are therefore more susceptible to noise and data errors. To provide an example of how QAM operates, the table below provides the bit sequence and the associated amplitude and phase states. From this, it can be seen that a continuous bit stream may be grouped into 3 and represented as a sequence of 8 permissible states. So the diagram below show the constellation diagram for a variety of format of modulation. So the constellation diagram show the different position for the state that within different QAM, quadrature amplitude modulation as the order of the modulation increase, so does the number of points on the QAM constellation diagram. Why QAM called combined of ASK and PSK? So quadrature amplitude modulation use the phase and amplitude of the carrier signal to encode data. QAM finds widespread use in current and emerging wireless standard, including Wi-Fi, digital video broadcast, DVM, WiMAX, IEEE 802.1, and HSDPA and HSUPA. The QAM modulation scheme encodes data by varying both amplitude and phase of the carrier signals. Thus, it's sometimes viewed as a combination of ASK and PSK modulation. So this is the combination, and we call the combined ASK and PSK, that is the QAM. A modulated carrier signal can be expressed in terms of components as AC cos 2 pi fc t plus theta and equal to I cos 2 pi fc t minus q sin 2 pi fc t, where I is the AC cos theta and AC sin theta, q equal to AC sin theta. In quadrature amplitude modulation, conclusion is an important modulation scheme with many practical applications. So including current and future wireless technology, some example of communication system that use QAM are Wi-Fi, cable modems, and digital video broadcasting, and also by Max. So that is the conclusion of QAM modulation technique. Now we discuss about the MSK modulation, minimum phase shift key modulation in digital modulation technique. So MSK is a type of continuous phase frequency shift key that was developed in the late 1950 and 1960, similar to OQPSK, offset quadrature phase shift key. So MSK is encoded with bits alternating between quadrature component with the Q component delay by half and symbol period. So MSK is a special form of binary CP FSK and therefore CPM, in which the modulation index H equal to 1 by 2. The phase of the carrier in the interval T is less than or equal to n plus 1 into T, or and T is greater than nt. So this is the uh, interval of the carrier. So phi t I equal to 1 upon 2 pi summation of minus infinite to n minus 1 ik plus pi inq t minus nt, and also qn plus 1 upon 2 pi in t minus nt upon t, where t is the greater than or equal to nt and less than or equal to n plus t. So the modulated carrier signal is st will be a cos 2 pi fct plus theta n plus 1 upon 2 pi ia t minus nt upon t. So the modulated carrier signal also a cos 2 pi fc plus 1 upon 4 pi in into t minus 1 upon pi and in plus theta n. The expression indicates that the binary CPFSK signal can be expressed as a sinusoidal having one or two possible frequencies in the interval of nt and n plus 1 into t. If we define these frequencies f1 equal to fc plus 1 upon 40 and f2 equal to fc minus 1 upon 40, then the binary CPFSK signal may be written in the form SIT equal to a cos 2 pi FIT plus theta n plus 1 upon 2 n pi minus 1 over I minus 1, where I is the equal to 1 and 2. Y binary CPFSK with H equal to 1 by 2 is called minimum shift key MSK. So because the frequency separation del F equal to F2 minus F1 equal to 1 upon 2T and del F equal to 1 upon 2T is the minimum frequency separation that is necessary to ensure the orthogonality of the signals S1T and S2T over a signal interval of length T. The phase in the nth signal interval is the phase state of the signal and result in phase continuity between the adjacent interval. Consider a continuous phase frequency shift key CPFSK signal which is defined for the interval t is less than equal to tv and greater than 0 as follow st equal to under root 2 EV upon TV cos 2 pi F1 T plus theta 0 for the symbol 1 and ST equal to under root 2 EV upon T cos 2 pi F2 T plus theta 0 for the symbol 0. So EV is the transmitted signal energy per bit. TV is the bit duration here. The theta 0 is the phase, denote the value of the phase at time t equal to 0, sum of the past history of the modulation process up to time t equal to 0. Another useful way of representing the CPFSK signal ST is to express it in the conventional form of an angle modulated signal as follow. ST equal to under root 2 EV TV cos 2 pi FCT plus theta T. Theta T is the phase of ST. When the phase theta T is continuous function of time, so we find that the modulated signal ST itself is also continuous at all times, including the inter-bit switching times. So the phase theta T of CP FSK signal increase or decrease linear with time during each bit duration of TB second. So theta T equal to theta 0 plus minus pi h T upon TB, where T is less than or equal to TB and greater than or equal to 0. The plus minus sign correspond to sending symbol 0 and 1. So we can find that Fc plus h upon 2TB equal to F1 and F2 equal to Fc minus h upon 2TB. We thus get Fc equal to 1 upon 2 F1 plus F2 and h equal to TB F1 plus F2. So these are the relation between and frequency Fc and a bit duration TB and different frequency F1 and F2. H is the referred to as a deviation ratio. So then with H equal to 2, the frequency deviation equal half that bit rate. This is minimum frequency spacing that allow the two FSK signal representing symbol 0 and 1 to the coherently orthogonal. Now at time t equal to TB, then theta TB minus theta 0 equal to pi h for symbol 0 and minus pi h for the symbol 1. This is to say the sending of symbol 0 increase the phase of a CP FSK signal ST by the pi h radians, whereas the sending of symbol 0 reduce it by an equal amount. Now there is a minimum phase shift key MSK heighten phase trails, and these are the represented in this graphical representation in between different value of h and the different time duration of TV. Now phase trails of sequence 110, 100 or h equal to 1 upon 2. So this is the phase trellis of the 110, 100 sequence, and we may express the CPFSK signal ST equal to under root 2 EB TV cos theta t and cos 2 pi FCT minus under root 2 EB TV sin theta t multiply sin 2 pi FCT. So the ST equal to S1 cos 2 pi FCT minus SQ sin 2 pi FCT. So this is the CPFSK signal ST. Consider first the in-phase components SI with the deviation ratio H equal to 1 upon 2. So theta t equal to theta 0 plus minus pi t upon 2tv, where t is the greater than equal to 0 and less than or equal to tv, where the pulse minus sign correspond to a symbol of 1 and 0. So a similar result holds for theta t in the interval minus tv, between minus tv and 0, except that the algebraic sign is not necessarily the same in both intervals. So since the phase theta t, sorry, theta 0 is 0 or pi depend on the past history of modulation process. So we find that in the intervals minus tv to plus tv, the polarity of cos theta t depend only on theta 0, regardless of the sequence of 1 and 0 transmitted before the or after t equal to 0. Thus, for t is less than equal to tb or greater than minus tb, the in-phase component SIT consists of a half-cycle cosine pulse defined as follow: SIT equal to under root 2 EV TV cos phi t equal to under root 2 EV TV cos theta 0 multiply cos phi t upon 2 TV. And also this will be equal to plus minus under root 2 EV upon TV cos phi t upon 2 TV, when t is less than tb or equal to tb and greater than or equal to minus tb, where the plus minus sign correspond to theta 0 equal to 0 and theta 0 equal to pi. So this is the value of theta 0 and pi. Similar for the time duration between 0 and 2 TV, the quadrature component SQT consists of half cycle sine pulse whose polarity depend only on theta TV, defined as follow: SQT equal to under root 2 EV upon TV sine theta t equal to under root 2 EV upon TV sine theta TV multiply sine pi t upon 2V. And also this will be equal to plus minus under root 2 EV TV sine pi t upon 2 TV when t is the between 0 and 2 TV. So where the plus and minus sign correspond to, and the theta value is pi by 2 and the minus pi by 2. This is the value of theta, minus pi by 2, 2 plus pi by 2. MSK signal may assume any one of four possible forms. First one is the phase theta equal to 0 and theta TV equal to pi by 2, then corresponding to the transmission of symbol 1. Second, the phase theta equal to pi and the theta TV equal to pi by 2, then corresponding to the transmission of symbol 0. Next, in third, if the phase theta 0 equal to pi and theta TV equal to minus pi by 2, then corresponding to the transmission of symbol 1. And fourth and last, if the phase theta 0 equal to 0 and theta TV equal to minus pi by 2, then corresponding to the transmission of symbol 0. So there are four possible forms of the MSK in which different phase angle and different bit time duration is taken for the different possible forms. Define the orthonormal basis function phi 1 t equal to under root 2 tv cos pi t 2 tv multiply cos 2 pi fct, time interval between 0 and tv. And second one is q2t equal to under root 2 upon tv sin pi t upon 2 tv multiply sin 2 pi fct, and time is also t between 0 and tv. From multiply of uh, these two, we have st equal to s1 phi 1 t t plus s2 uh, phi 2 phi 2 t, and the time interval between the 0 and tv, where the coefficient s1 and s2 are related to the phase state theta 0 and theta tv respectively. So S1 equal to minus integration of ST phi 1t dt from minus TV to TV equal to under root EB cos theta 0 when t is the between minus TV to TV, and S2 equal to integration from 0 to 2 TV ST phi 2 t dt equal to minus under root EB sin theta TV, and small t is the uh, between 0 and 2 TV. So both integral are evaluated for a time interval equal to twice the bit duration. Both the lower and upper limits of the product integration used to evaluate the coefficient S1 are shifted by the bit duration TB with respect to those used to evaluate the coefficient S2. The time interval t is less than tb or greater than 0, for which the phase state theta 0 and theta tb are defined, is common to both integrals. So this is the signal space diagram for the MSK systems. This represents the minimum phase shift key signal space diagram. In QPSK, the transmitted symbol is represented by any one of the 4 message points, whereas in MSK, one of 2 message points is used to represent the transmitted symbol at any one time. So there are transmitted binary symbols, that is the 0101, and phase state in radians. Theta is the 0, pi, pi, and 0, and theta TV phase state minus pi by 2 to plus pi by 2, and the coordinates of message point S1 and S2. S1 is the plus under root EB2 minus under root EB, and similar the value of S2 under root EB and minus under root EB. So these are the symbols represented in by the 4 message points. There are input binary sequence waveforms of scale time function S1 phi 1t and waveform of scale time function S2 phi 2t, and the waveform of the MSK ST obtained by adding the S1 phi 1t and S2 phi t2 on a bit by bit basis. So this is the input binary sequence that is represented by the different waveforms. Now, in coherent detection of the MSK signal, in the case of AWGN channels, the received signal is given by xt equal to st plus omega t, where st is the transmitted MSK signal and omega t is the sample function of a wide Gaussian noise process of zero mean and power spectral density and not divided by 2. For the optimal decision of theta 0, x1 equal to minus tv to tv integration. So xt phi 1t dt equal to s1 plus omega 1 when t is less than tv or greater than tv minus tv. If x1 greater than 0, then theta 0 will be 0 and x1 less than 0, then the theta will be pi. So in coherent detection of the MSK signal, for the optimum detection of theta TV, x2 integration from 0 to 2 TV of xt I 2t dt equal to s2 plus omega 2, the time interval between 0 and 2 TV. And there are two conditions. If x is greater than 0, then theta tv equal to minus pi by 2. And if x2 is less than 0, then theta tv equal to pi by 2. So error probability of MSK PE error probability 1 upon 2 ERFC of under root EV upon N naught, which is exactly the same as the for binary PSK and QPSK. So that is the block diagram of for the MSK transmitter. In this block diagram, there is a different two band pass filters and two summations and also two multiplication network and and also one summation network at the output. At the input, the signal is applied to multiplication network. The signal is cos 2 pi fct and another signal is cos pi t on 2 tv. And this signal applied to the two band pass filter which have the frequency f1 and f2. And the output of these filters is again applied to the two different summations. And then after the summation, the output of this summation phi 1t and phi t2 also multiplied by the alpha 1t signals and alpha 2 t signals in the multiplier network. And after multiplication of two signals in two different multipliers, then the output taken from the summation of these two outputs of the multiplier signals, and that is the MSK signal. That is the output taken from the summation of the output summation network, that is the ST. So this is the block diagram of MSK transmitter. Now block diagram for the coherent MSK receiver. So in this block diagram, there are two multipliers and two integrator network, and two is the decision device network, and one is the logic circuit for interleaving phase decision. So the input is applied to the two multiplier xt, and the output of these multiplier is again applied to the two integrators, and the output of these two integrators x1 and x2 applied to the decision device, and the also a threshold equal to 0 applied to these two decision devices also, and the output of these decision devices phase estimate theta 0, and second output is the phase estimate delta TV, and these two outputs of these two decision devices is applied again to the logic circuit for interleaving phase decision, and the output of this logic circuit for interleaving phase decision is the in the form of binding sequence. So here is the Coherent MSK receiver block diagram explanation, and that is the power spectra of the MSK signals that is represented by in this graph. And so the uh, QPSK and MSK does not produce as much interference outside the signal band of interest as QPSK. So SB a signal of SVF equal to 2 psi g phi upon 2 TV equal to 32 EB upon pi square cos 2 pi TV F upon 16 TV square F square minus 1 ka whole square. So this is the power spectra uh, density representation of MSK signals. MSK may also be represented as a form of four-phase PSK. The equivalent low-pass digitally modulated signal in the form of Vt equal to summation of minus infinite to infinite I 2n g t minus 2n t and minus j I 2n plus g t minus 2n t minus t, where gt is the sinusoidal pulse. So gt equal to sine pi t upon 2t when the value of t is less than 2t or greater than 0, and gt equal to 0 otherwise. So this type of signal is viewed as a four-phase PSK signal in which the pulse shape is 1/2 cycle of a sinusoidal and 0 to pi. The even numbered binary value plus minus 1 symbol I2n of the information sequence IN are transmitted by the cosine of the carrier, while the odd number symbols I2n plus 1 are transmitted by the sine of the carrier. The transmission rate on the two orthogonal carrier components is 1/2 t bits per second, so that combined transmission rate is 1/t bits per second. Note that the bit transition on the sine and cosine carrier components are staggered or offset in time by t second. So for this reason, the signal st equal to a summation of minus infinite to infinite I to g 2 ng t minus 2 nt multiply cos 2 pi fct plus summation of minus infinite to infinite I 2 n plus 1 g t 2 n t minus t multiply sine 2 pi fct is called offset quadrature PSK, OQ PSK, or this is the PSK or SQ PSK. So in next representation of an MSK signal as two quadrature modulated binary PSK signal, the corresponding sum of the two quadrature signal is constant amplitude frequency modulated signal. This is the representation of in phase signal components and quadrature signal components, and MSK signal sum of is the waveform A and B, and waveform C is the MSK, that is the sum of two A and B waveforms. Compare the waveform for MSK with OQPSK pulse GT is rectangular for t is less than 2t and greater than 0, and with conventional QPSK pulse GT is rectangular for t is less than 2t or greater than 0. All three of modulation method result in identical data rates. The MSK signal has continuous phase. The OQPSK signal with a rectangular pulse is basically two binary PSK signal for which the phase transition are uh, staged in time by t second. Thus, the signal contains phase jump of plus minus 90 degree. The conventional four-phase PSK QPSK signal with constant amplitude with contains phase jump of plus minus 180 or plus minus 90 every 2t seconds. So there are in this waveform representation, compare the waveforms of different MSK with QPSK and QPSK. So first way the show the MSK, second we show the offset QPSK, and third one show the QPSK. So they are the compare the waveform for MSK with QPSK and QPSK. And this is the also graphical representation of GF versus and frequency for the MSK and FFSK and also QPSK and OQSK. These are the reference books for this topics, and there are some multi-choice questions. Thank you very much.